I will start recording. Today is 3rd of November 2023. Now time is 10. And welcome. This is EE3203 or 3252 electrical and electronic measurement. Under that lecture 9, I think. Lecture 9, yes. Then unfortunately, I have to say that we have to move to this online system for today, and I think the standard data charges may apply for you. Okay? I think this is connected to Zoom global network via data centers in Singapore. Therefore, rate charges may apply. Then in the last lecture, we discussed about the functionality and use of harmonic distortion analyzer. We discussed about the linear load and non-linear loads. We need to discuss today. Non-linear loads. I think you can see. And the non-linear loads don't have a constant relation with the current and voltage along the alternating period. Let's say you have this kind of what is this called? Diode rectification circuit. Then these are three phases, and your L here. Then I will draw the diode. Of course, you can learn these things during the 5th semester in electrical students, for electrical students, but not for computer students, I think. Here you can put smoothing capacitor, and in addition some load. Okay, I think you can see my what I am writing. I spotlighted the screen for you. Then I'll connect it here. Then you can ground all the things. So you supply voltage in this manner. This is T, and this is voltage, supplied voltage. The current flow through this load. This you can write in this way. This kind of graph, and T, current flow through it. And so we can see the supplied voltage and drawing current is not a proportional one. There is a non-sinusoidal waveform and referred to as complex waveform. This one is referred to as complex waveform. And it is non-sinusoidal. Non-sine wave. Therefore, this current said to contain harmonics. Okay. Then by power supply or equipment operating within the system may produce frequency effects. That's how higher order frequencies generate within the system. By power supply or by equipment operating within the system may produce frequency effects. Frequency effect, that's how higher order frequencies are generates within the system. That's how harmonics are generated. And we can apply Fourier analysis for periodic signal, and any complex periodic signal can be obtained as the addition of different pure sinusoidal waves at different frequencies and amplitude in multiple of the fundamental frequency. It says that this kind of one, you know, the Fourier analysis, we can fx, we can denote it as a0 plus a1 sine omega naught t plus a2 sine 2 omega naught t plus likewise up to an, and in addition we have b1 cos omega naught t plus b2 cos 2 omega naught t, likewise up to n. Then that's what I said, that the addition of different pure sinusoidal waves at different frequencies and amplitude. These multiples are called harmonic. These multiples are called harmonic. Actually, this one is the fundamental, and the rest of the things are called harmonics. Harmonics. And if I analyze it further, the term a1 cos x plus b1 sin x in Fourier series is called the fundamental of first harmonic. The second harmonic, the second term, a2 cos 2x plus b2 sin 2x in Fourier series is called the second harmonic, and so on. Okay. So now I relate the Fourier series here. So in addition to this one, I will write I, current term, IT is I naught plus sigma n is equal 1 to n, capital N, then an sine n omega t minus psi n. This is general term. Here I naught is 0 Hertz component. Simply it is DC or mean value. This term, total term, is the signal, and when n is equal 1, you receive fundamental signal, and from n is equal 2 to n infinity, it is called harmonics. Then you have one signal here. And you can decompose it into fundamental signal plus some kind of harmonics. These are called harmonics, and this is called fundamental signal. This is the total signal. Then here we have phi, and this is called phase displacement for each harmonics. And yes, that's all. And now you can suppose that you can assume that this I naught or DC component of the signal is 0. Therefore, you can assume a signal with no DC component. Then IT, you can write it as 0 plus the remaining term. n is equal 1 to capital N, then I n t. The total term I denote in this way. Okay, this way. Then again I will separate this one with I1t plus the remaining n is equal to capital N I n t. This is the fundamental. The frequency of the signal is f1 and omega 2pi f1. These are the harmonics and remaining things. Okay. Then what we can do is I need to show you the second harmonic, third harmonic and fourth harmonic. Therefore from here I will again write these terms. I1t is A1 sin omega t. The I2t A2 sin 2 omega t. Then A3 sin 3 omega t plus likewise. Okay, this is the fundamental f1 and this is 2 times f1, frequency is 2 times f1, and here the frequency is 3 times f1, and remain likewise we have 4 times 5 likewise. Okay, f1 2 times f1, 3 times f1. Then this is said to be first harmonic, and has the supply frequency, same frequency as the supply, and supply frequency, okay, the lowest frequency. Then the second term, this one is called second harmonic, this one called third harmonic, and likewise. These harmonics, however, you can see this is F1 and multiplication of F1, voltage and currents that are operate at a frequency that is an integer multiple of the fundamental frequency. Integer multiples. These are integer multiples. Therefore, I need to tell you that the harmonics classified by with the name. Second harmonic, third harmonic. Okay. So I have one example question, and fundamental frequency of Sri Lanka power system is 50 Hertz. Then fundamental, actually this is not example, it's clarification. Okay, fundamental signal or first harmonic is 50 Hertz. Then if you need to find second harmonic it is 100 Hertz. This comes as 2 times 50. And third harmonic is 150, 3 times 50 Hertz. Okay. Then we need to see the complex waveform due to harmonics. In books, okay, reference book, it mentions some kind of graph, and I have modeled it. I will share the screen. This is the system I modeled. And I think you can see my shared screen. Do I need to stop my video? Can you see me? Oh, can you hear me?
Yes.
Okay. Can you see my screen?
Yes, sir.
Okay. Then I will run this simulation. What I have done was I created sinusoidal waves, sine wave, and amplitude is 1. Here the frequency is 50. I keep this one as fundamental signal source, and I modeled the second harmonic sine wave, and frequency is 100. Here the frequency is 150. Here 200, 250. Here 300. Okay. Then I will connect these switches, and I will observe using and I will run this one. Yes. I will run this one. And the only signal you need to see here is this one. And I think I need to increase the time division. This the wave connected here. That means I can look at the second harmonic that means 100 hertz. Okay, now the wave pattern is somewhat different. Third harmonic, fourth harmonic, fifth harmonic, sixth harmonic. The third one. Okay, that's all. I made a mistake. I should not close the signal. If so, I need to again. And we can't hear you clearly. Now, yes, I think it is been due to this bandwidth issue, so I will stop sharing now. What I did was I connected fundamental signal, and you should be able to see very clear signal. Then I connected second harmonic, then the wave pattern is little bit changed, and thirdly I connect third harmonic, then the wave pattern distorted more. Okay, distorted more. I think you can clear now. Then the wave patterns, waveforms I shown you. Then in generally symmetrical waveforms, only odd harmonics may appear. Odd harmonics, we have odd harmonics and even harmonics. Okay. Odd harmonics mean third harmonic, fifth harmonic, seventh harmonic, likewise. Even harmonics means second harmonic, fourth harmonic, sixth harmonic, likewise. Then For symmetrical waves, we only have odd harmonics. Odd harmonics only. For asymmetrical waves, and you can see odd harmonics plus even harmonics. Odd harmonics and even harmonics, both waveforms you should be able to see. And for symmetrical waves, you should be able to see only the odd terms only. Okay. Then, in addition, we have triple enharmonic video blurring. Now you can hear my voice clearly, isn't it? Can you hear my voice clearly? Yes, audio is clear. Now the problem is with increased font size. Okay, font size. Blurring. I think I stopped video settings and no blurring effect is there. Blurring effect is not there. Font size I will increase. Font size I will increase. Font size I will increase. For symmetrical waveforms, we only see odd harmonics. For asymmetrical signals, we should be able to see odd and even harmonics. Okay. Then we have triple enharmonic. This term says that multiple of third harmonic. Multiple of third harmonics. Now, is it okay? Can you see?
Yes, sir.
Okay. Then multiple of third harmonic, that means third harmonic, sixth harmonic, ninth harmonic, 12th harmonic likewise. Okay, triple enharmonic. In power electronics, you may hear this triple enharmonic and memorize. It says that third harmonic, sixth harmonic, ninth harmonic, 12th harmonic. Due to these harmonics, the output waveform is distorted, and this effect is called harmonic distortion. Due to these harmonics, the output waveform is distorted. I shown you using the Proteus file, and this effect called harmonic distortion. And there are different types of distortions: the frequency distortion, the second one phase distortion, and amplitude distortion. The fourth one is intermodulation distortion, and fifth one called crossover distortion. And we are discussing about frequency distortion. So then we have harmonic indicators and measurement. Harmonic indicators and measurement. Harmonic indicators and measurement. We need to indicate and we need to measure the harmonic. The first parameter or first indication method is individual harmonic percentage. Individual harmonic percentage. The term is the amplitude value of a particular harmonic, and IN can be expressed in relation to the fundamental I1. IN, and the units is percentage, and you can denote it as 100 times. This 100 means 100 percentage times IN over I1. Here IN refers to amplitude value of a particular harmonic. Amplitude of a nth harmonic, and I1 is amplitude of fundamental. Amplitude of fundamental. Okay. Then if you need to find I2 as a percentage, and I2 over I1 multiplied by 100. So this is the individual harmonic percentage. Then the second visualization method is harmonic spectrum. So you are seeing this is harmonic order, and the y-axis is harmonic percentage, and 100 is the maximum value here, percentage one, and the first harmonic, let's say first harmonic, and second harmonic you may not have, and third harmonic it is I think 15, and fourth harmonic you may don't have, and fifth harmonic it is 12, and sixth harmonic you don't have, seventh harmonic you may have it as 9. This kind of, if you saw this kind of wave pattern, that is called harmonic spectrum. Then it's called harmonic spectrum. Then the third indicator is total harmonic distortion. Total harmonic distortion, or THD. Okay, then the total harmonic distortion means the ratio between the RMS value of all the harmonics and the RMS of the fundamental frequency. So we can denote THB as this term sigma n is equal to capital H, okay? Capital H is equal to simple n and yn yh over y1 and multiply, take the square and total square root. Okay, then this is a general term, okay? This is a general term, and if you see it y1, here no meaning. Yes, of course we can show it later, okay? I will show you later. Then can you see my paper? Yes. Okay. Then I will expand the previous equation. Okay, I will expand the previous equation and we can denote y1 squared plus y2 no y1, okay? No y1 here. y2 squared and y3 squared plus yn squared, and take the square root, and you have to divide it by y1. But you should memorize these, all the terms are RMS values, okay? These are RMS values. Okay, so this n could be 50, maximally could be 50. N could be 50 maximum. The more than 50, you can assume that all are more or less equal to 0. Okay, from here what you have to understand is this THD value can exceed 1. The THD can exceed 1, and it could be 0. THD could be 0, but minus no, okay? No negative number. If you receive a negative number, that means however you did some kind of mistake, okay? But it is not applicable to decibels. And this general term, you can divide it into two parts. That is current harmonics and voltage harmonics. You can see on your screen. Okay, then for current harmonic, if it is current harmonic, then this term is derived THDI is equal square root of summation H is equal to N and IH squared IH over I1 squared. For voltage, THDU or THDV is equal summation square root of summation h is equal to n u h over u1. And so here, if the current harmonic is, you are measuring current harmonic, this is the THDI, and if it is below than 5%, if it is below than 5%, it is normal, and no risk of malfunctioning. This is 5%, okay, 5%, and it is normal and no risk of malfunctioning. Then if it is between 5 to 8%, significant, and some malfunctions are available. And if it is more than 8, then if it is more than 8, then major harmonics distortion is available. Major harmonic distortion is available. Okay, so higher malfunctions are there. Higher malfunctions are there. Then if you referred it with this voltage harmonic, if I draw the curve THDU, and if it is below than 10%, it is normal, and if it is in between 10 to 50, not 15, 50, okay, it is significant, and more than 50, it is major harmonics, okay. Then I shown you this example. This one, and one example. By using harmonic spectrum mentioned above, find the THD value. So you can write, substitute to the equation. Substitute to the equation. The second harmonic is 15 and squared it, and say third harmonic is 12 and squared it, and this is second, and this is third, and fourth harmonic, this is third harmonic, and this is fifth harmonic, and this is seventh harmonic is 9, and square it, and take the square root and divide by the fundamental 100, and you should be able to get value as 21.21. You can find this kind of relation as well. The next question, compute total harmonic distortion of a signal that contains first harmonic RMS value as 10, second harmonic RMS value as 3 volt. Netmi De Silva, are you willing to say something?
Yes, sir.
Oh, what? Are you willing to say something? Yes, sir. Then we are. Okay. Then second harmonic RMS value is 3 volt, and third harmonic RMS value is 1.5 volt, and fourth harmonic value is 0.6 volt. Then you can find THD, and since this is given as RMS value, you no need conversion of amplitude to RMS. Okay, amplitude to RMS. And if I give you amplitude value, you should be able to convert it. Okay, and show this step in the exam. So 3 squared, 1.5 squared, and 0.6 squared, and square root, divide by 10 and multiply it with 100. Then you should be able to get 34.07. The next example, if a pure 100 Hz sine wave series if a pure 100 Hz, no, I will skip that question. Actually, I need to check it. That's why I am skipping it. Okay, another example, amplitude of a distorted sine wave is listed. Harmonic and amplitude. First harmonic is amplitude is 3.08 volt. The third harmonic 0.308 volt, and fifth harmonic 0.159. Seventh harmonic 0.090, and ninth harmonic 0.0487, and 11th harmonic 0.0253, 13th harmonic 0.0164, then 15th harmonic, it is 0.01, and more than above harmonics are more or less equal to 0. Then find the THD value. Okay, did you write the question? Can you write? Can you see these values? Huh? Can you see these values?
Yes, sir.
Eh? I cannot hear. Can you see these values?
Yes, sir.
Okay, then okay, the 15th harmonic is 0.01 and above is equal to 0. Then here we have a derivation. Okay, here we have a derivation. The normal in previous case I define what is THD. THD is V2 RMS value and square it, and V3 RMS value and square it, and V4 RMS value and square it likewise up to n, and take the square root and divide it by V1 RMS value. This is the definition I say. Now you have given amplitude V peak or amplitude V peak, and if you divide it by root 2, then you will receive VRMS value. VRMS value. If it is a sinusoidal signal, then you can substitute this term here, V peak value of 2 and divide by root 2 and square it. Then V peak value of third harmonic and divide by root 2 and square it likewise up to n and take the square root, and you can divide it by V peak value of first harmonic and root 2. Okay. Then what happen? You can take root 2 out, and root 2 will be cancelled out. That's why we can use RMSO peak value or amplitude, but you have to clearly mention this conversion. Okay, clearly mention this conversion. Okay, likewise you can do rest of the question. You can get the THD value as 11.8%. Okay. Then I need to show you the LT Spice software. LT Spice software. So that's all. And now I will stop the video. And I will share my screen. And you can go to internet. And search LT Spice download. Then you will receive a link under www.analog.com. Analog.com. If you go there, you can see download links. Download for Windows if it is Windows, and Mac if it is Mac. Then this LT Spice is an analog electronic circuit simulator software, and it's free software. Okay, free software. And I already downloaded and installed LT. Downloaded and installed. This is the front page, and you can create new schematic, and here in the toolbar, in this toolbar, you can see the basic components. If it is a wire, then you have wire here. If it is ground, then the ground terminal. If it is resistor and capacitor and inductors and diodes and other components, you can drag and drop from here. Drag and drop from here. And so go to this component, go to this component, and you can find here voltage. That means voltage source. Component and voltage, and press OK. Then you are receiving voltage source. So I will press escape button in order to cancel the next. That means creating next source. Then I need to ground this negative terminal. So we have here the ground terminal, and on top of this box I will create it. Then press escape. Then I will right click this voltage source, and from this advanced select this side. And you can set DC offset to 0 volt, and amplitude is 5, and frequency is 50. Then I will press OK. Then we can run this simulation. By pressing this button, run button. Okay, it asks what is the stop time, and I will set stop time to 5 and press OK. Then your graph should be whatever the graph should be displayed here. Still I did not define what is this graph. Okay, so go to here and you can see my positive mark, plus mark change to a probe. If I press this one, I am seeing here the oscilloscope pattern, oscilloscope wave. I will increase this one. Of course, I am seeing this kind of sine wave. So I created 5 volt amplitude, and you can see the what is period. Okay, period. You can go to that previous simulation window and if you need to change the stop time, right click here, and here edit simulation CMD. Hover over the power supply node point at the positive side and see the probe head and click it. Yes, I shown you this one. And now we can see the sine wave. Okay. Then I will change. Right click here, DC offset to 3 volt, and press OK. Then run it. Then you should be able to see this kind of wave, and DC offset is in 3 volt. 3 volt. Then right click on graph area, right click on graph area and view, and you can see here FFT. How? Right click on graph area and view, and here FFT, click it and select the wave VNC01 and press OK. Then you should be able to see the FFT wave, or what is we call normally frequency domain signal with decibel and frequency. Okay. Then our signal frequency is 50 hertz. 50 hertz. You can see here 10, 20, 30, 40, 50. 50, yes, it is 50. And I think this is 100, and this is 200, 300, 400, 500, 600, 700 likewise, and 100 and 200. In between those two we have another ripple. That means I think this is 150 hertz. 150 hertz, because this is pure sinusoidal. This is pure sinusoidal one, and this is symmetric one. We should have only the odd harmonics. Okay, so now you can see very in MATLAB also we can model this one, but it is complex. It is very complex. The spectrum analyzer is very complex one. Therefore, that's why I am not using that software. Of course, we can use MATLAB, but LT Spice is a very industry used one, and analog we can model or simulate analog electronic circuits. So you have one task. Upload a screenshot, and that screenshot should contain this FFT graph and the name of the software is LT Spice. Here you can see LT Spice. Here you can see LTSPICE. Okay, CE. Then this kind of view, I can see the voltage source, I can see the time domain wave, I can see the FFT domain wave, fast Fourier transform wave. So take any screenshot, press Windows and print screen. So that why I am saying that I should be able to see this date and time. Okay, date and time. What are the applications you opened? එතකොට අනිත් එක්කෙනාගෙන් copy කරේ නැහැ කියලා I can understand. So that's why I am telling you to take all these screenshots. ඒ කියන්නේ මේ part එකක් ගන්න එපා. Don't take a part of the screen. තියෙනවනේ මොකද්ද screen snipping tool එකකින් දාලා ගන්න එක part එකක්. Take whole this screen. Okay, then take your registration number let's say your registration number is who is this one, and then we select 4408, then 4408. Okay, then take your registration number. If the last bit here it is 8, and if it is 0, then generate triangular wave. If it is odd, then generate sine wave. If it is an even number, then generate square wave. You understood what I am saying? You understood what I am saying? Let's say your registration number 4408, and take last digits. If it is 0, you have to generate triangular wave. Triangular. If it is odd number, then generate sine wave. If it is even number, then generate square wave. SQARE, square wave. Then take your last, this is the wave type. And again take last 3 digits. And this is your frequency. This is your frequency. And see whether you can do it or not. So generate a FFT representation and normal oscilloscope wave, and keep FFT graph and voltage source oscilloscope wave and in one page, and take a full screenshot. And I should be able to see toolbar and date, time, and likewise. By doing that, I am ensuring you don't copy with others. And rename the image. You are taking some kind of image, either PNG file or JPG file, PNG or JPG, and rename that one to your registration number, in this case 4408.png, and upload it to LMS. I have already created the link in the LMS. Upload it within Monday. Deadline is Monday. Okay. Deadline is Monday. The amplitude, yes, very good, very good question. And keep what I used. Offset you can set to 0, and amplitude is 5. Amplitude is 5. Is 5. Actually, you can find out many tutorials regarding this LT Spice tutorials. this one. So I know you can explain this one. I know you can explain this one. So that's all about the assignment. That's all about the assignment. Actually, this is not the assignment I need to give you. I will give you it later, and you should complete this one. You should complete this one. Otherwise, we can see it later. Okay. Then I will stop sharing my screen. Stop sharing my screen. Stop sharing my screen. And again, I have another question for you. Another question for you. Another question for you. Another question for you. Question for you. Question for you. 8. Write down example. For a periodic function shown in figure below, find the amplitude of the first, second and third harmonic component. Find the amplitude of the first, second and third harmonic component. The fundamental frequency is 10. Fundamental frequency is 10. Fundamental frequency is 10 Hertz. The curve is something like this. Curve is something like this. I will do another lecture for graph plotting. You have several graph points and how to select best curve. How to select best curve, I will do it later. And in generally, you should know we need to draw a graph by points manner. First, we should draw the points, then draw it with curve. This is time axis, and this is amplitude. Amplitude. I will close my screens. Okay. Then this is in unit seconds and amplitude is in volts. Then here it is 3, here it is -3, and this time value is 0.05, this time value is 0.1. And this is the question, and you can answer, and I will solve this one. Fundamental frequency I given you as 10 Hertz, and angular frequency omega is 2 pi f, and 2 pi f is 10. Here you receive 62.83 rad per second. 1 mark. 1 mark. Then I will denote this curve part as 1 and this part as 2. For part 1, time from 0 to 0.05, the function ft is 60 times t, and the t is 0 to 0.05. This is equation 1. And for second part, the time is 0.05 to 0.1, and ft is 60t minus 6, and this is range from 0.05 to 0.1. This is equation 2. Then the average value of the function, is 0 for any cycle. Then according to your Fourier series theories, the A naught is 0. Okay, A naught is 0. We have to use this kind of equation. Ft is equal A naught A1 cos omega naught t. In previous case, I think I made a mistake in previous equations. I denote it as A1 cos, A1 sin. Yes, A1 sin, but here it is A1 cos. Okay, no matter. Okay, A1 cos omega t and A2 cos 2 omega naught t, likewise up to n, and then B1 sin omega naught t, then a B2 sin 2 omega naught t plus up to n. Okay, here A naught, you have an equation 1 over the period of the signal and multiply it with 0 to the period time, and ft dt. If you calculate this one, you should be able to receive the A naught coefficient, this one, and an term you can receive 2 over period 0 to period, and ft cos n omega naught t dt. So here period is t, and bn 2 over period anukala 0 to period ft sin n omega naught t dt. So we found out A naught is 0 due to average value of the function is 0. Mark me sadya, the average value of the function is 0. Then ft is the ft curve, this one ft is considered to be an odd function. Why? Odd function means ft is equal minus f minus t. If this is satisfied by using this function curve, then it's that function is said to be odd function. Odd function. Odd signals, even signals, I think you can remember during signal and systems. Then this is odd function. Therefore, we can represent the wave only with sine terms. We can represent, since this is an odd function, we can represent wave with sine terms, and cos terms will be 0. Cos terms 0 means these become 0. These terms will become 0. Therefore, A1 is 0. A2 is 0. Likewise, up to AN is 0. You understood? AN becomes 0. So we have found out A0, A1, A2 up to AN. Now we have to find out B1, B2 likewise. So when n is equal 1, B1 is 2 over period. Here the period of the function is again repetitively 0.1, and integration from 0 to the period is 0.1, and ft there are two functions. ft2 is this one. Therefore ft sin n means 1 here, omega naught t dt. So I can integrate this term up to 0.1 by using 2, from 0 to 0.05, this one term, and from 0.05 to 1 it is another term. So 2 over 0.1, 0 to 0.05, ft is here now 60t, and sine omega t dt plus integration from 0.5 to 0.1, 60t minus 6, 60t minus 6, 60t minus 6. Can you see my screen?
Yes.
Okay, 6 and sine omega t dt. Then you can take one final answer. It is 1.9098. Therefore B1 is this one. B1 is this one. Likewise, you can substitute n is equal to, and you can receive B2 as minus 0.9549, and when you substitute n is equal 3, you receive B3 and it is 0.6366. And question asking about, for a periodic function shown in figure below, find the amplitude of first, second and third harmonic component. First, first, second, third harmonic component. Okay, now I have integrated the Fourier analysis here. So I can ask many questions, okay? I can ask many questions. Okay, that's all for today. That's all for today. That's all for today. And thank you for joining. Thank you for joining. Your attendance will be recorded and I will take it. And thank you.